Hi, this video is a part of Machine Learning Algorithms from Scratch playlist. In this playlist, I explain different machine learning algorithms implemented from scratch using Python. You can download the relevant Python files from the link given in the description of each video. Note that I do not code along, rather I make use of pen for explaining the tricky parts of code so that you people can read the notebooks and understand them yourself and of course re-implement them yourself. I'm expecting my audience to be well versed with machine learning general understanding, and they just need little explanation and hints for implementing these algorithms from scratch. Now in this video, I'll explain development of advanced nearest neighbors algorithm based on spatial correlation structure. This spatial correlation structure is important. This algorithm is also well known with the name of ordinary Kriging. Now, in case of regression, simple nearest neighbors outputs the weighted average of its closest samples. The weight in that case is dependent upon only the distance. Greater the distance, lesser will be the weight, and vice versa. However, the problem in that is that in this simple implementation, they don't take into consideration the spatial correlation structure or the grade correlation structure. Why is that important to take into consideration, and what is basically it and how it looks and how it works? We will look at that. We will look at this theoretical part as well as the implementation part. Let's understand it in depth. Let's begin. Suppose we have two-dimensional data. We have x-axis, we have y-axis. Let me change the pen. Okay, so we have two-dimensional data, and we are considering these orange points to be training samples, and the size of orange point is actually showing the value of output. Greater the size, so greater the output. I'm calling the output here a grade. So for that reason, what I'm trying to find out is this grade correlation structure or the spatial correlation structure. Suppose we have to find out suppose our test point lie in this green circle or in this second green circle. So in both of these green circles, in these regions, in this region, the spatial correlation is toward northern easting. If you look at it, so the grade is actually increasing and has a correlation and has a structure in this direction, in direction of northeast, whereas the direction of this grade structure is towards northwest. If we look at it in this second green circle, so if we have to predict the value in this second green circle, we have to make use of different weights than this first circle, given the structure of the correlation, underlying correlation structure. If we make use of simple distances, it will be very crude. We are totally missing and we are totally ignoring this very important information. So it might be showing some pattern. It is some kind of a pattern, so we should make use of this pattern. Now, how will we calculate this the extent of this spatial structure and the direction of this spatial structure? For that reason, what we will do is we will calculate semi-variogram. We will use semi-variogram values for finding out this range and direction. The variogram modeling, which is very much well explained in books and videos, you can find out there, but I'll also explain here. Now, I'll explain it very fastly, so you can also, if you want details, you can also go out there and have a look at it. Now consider we have 470 training sample and we have 78,000 testing samples in this grid, regularly spaced. Suppose we are given, and if we are not given, we will create grid for that. I'll be also showing you the function for creating this grid of testing points in this region. Okay, now how will we find out the range and direction using semivariances? For that, what we will do is we will look at the maximum distance. Suppose the maximum distance between training samples is 100 meter. Now, if that is the case, and we want to look at the pair of samples which are 10 meter apart. Suppose we are looking at pair of samples which are 10 meter apart, and we are giving a tolerance of 2 meter. What does it mean? It means, and we are also looking at all the samples which are placed at -10 degree to 10 degree. So this is like from 350 degree to 10 degree. Both of these are actually equivalent things. Now, it means, this simple fact means, take all the pairwise samples which are placed -8 meters to 12 meters apart and are having angle from northing. So we are taking the angle from northing. This is also called azimuth. Okay, so take all pair of samples which are 350 degrees to 10 degrees apart and 8 meters to 12 meters apart. Now in that case, all of the pair of samples will be used for calculating a single value, which we will call semivariance. I'll explain that calculation later, but you need to understand that given maximum distance of 100 meter, this angle, this 0 degree angle and the tolerance of 10 degrees, this 10 meter lag distance and the tolerance of 2 meter, what do we mean by these values? What we mean is we want to extract pair of samples which are 8 meter to 12 meters apart and 350 degree to 10 degrees, having angle of 350 degrees to 10 degrees with an northing. All of those pairs, we will extract them out, we will use them for semivariance calculation. Now, if the maximum distance is 100 meter, then we will also use the lag distance of 20 meters, then 30 meters, then 40 meters, then 50 meters, up to 100. So in that way, we will extract out 10 different values, and these 10 values will be called, once plotted, experimental variogram. And based on this experimental variogram values, we will fit this blue variogram model. And there are 3 different variogram models, Gaussian, spherical, and I'll explain that. But once we have that variogram model, what does it mean? It means that now we have a model which can tell us the semivariance value, or the what you call the correlation structure, or the variances. So correlation and variances, they all are they all have a relationship. They are interchangeable. So given the distance of any pair of sample and given the angle, we can calculate this semivariance value. So this is important. So this is the main crux of it. Now, to calculate these things, so we will be needing 4 functions. First one is actually this pairwise distance. This is important. So this will be 470 cross 470, given we have 470 training samples. So this change in output is important. Change in grade is important because it is kind of it will be used extensively later. So one function will be representing this pairwise differences between training samples. The second function will be used to remove the diagonal elements, because at diagonal the difference will be 0, because it is the difference with itself, difference of samples with itself. Now, third, we will find out the angle with northing for each training sample. This is like finding azimuth, because that will be also used for extracting the samples out. Fourth, we will find out the Euclidean distance between training samples pair, that will be used for finding out the pairs at a specific lag distance. Now, in the loop, we will look at all the lag distances as we have already discussed. We will extract the pairs, we will count the number of pairs, we will sum the total change in grade that we have calculated already, that I told you that it is extensively used. Now this change in grade will be used, we will sum the total change in grade for those pairs, and we will divide this sum total change in grade by the number of pairs, and we will extract out this semivariance value for this specific lag. And for each lag distance, we will calculate this value and we will plot them. And once we plot them, so this semivariance values has actually structure. There are specific names for this semivariance structure. First one is called nugget. So this value, the value at first lag is actually called nugget, and the value where this increase has gone out, and this function has flattened out. So this value of semivariance is called SIL, and the range is the actually lag distance at which the function flattens out. So given this range, this SIL in nugget, we can calculate the variogram model. So once variogram model is fitted to it, then we have the power to calculate semivariance given any distance and any direction. Now then what we will do is create grid of 78,000 points in case we are not given. Then we will find neighbors for each test point, and once we find the neighbors, then for each test point we will calculate 2 distances. One, the pairwise distance of neighbors with itself, with themselves. Consider we have 10 neighbors for a specific test point, so it will be a 10 cross 10 matrix. Then we will calculate the distance of that test point with all the neighbors. So this will be 1 cross 10 matrix kind of a. Okay, then what we will do is we will use this variogram model to calculate, because these are distances, so we will use this variogram model to calculate the semivariance values. We also call that a covariance matrix. So these we will get these 2 covariance matrices for both of these distances, distance matrices. Once we have these distance matrices, we add Lagrange parameter for unbiasedness condition. This is a kind of a very minor detail, but you can look at it online. I won't go into the detail for that, but it's adding 1 at the end of the columns and adding 1 at the end of the rows and adding 0 at the extreme left and extreme bottom value. Now There is a mathematical formulation for that. You can look at it in any book. You can look at it in applied geostatistics book, any YouTube article, Google article, or YouTube video. Okay, once we have these matrices, we can find weight by taking inverse of pairwise covariance matrix, which was 10 cross 10 matrix, and dot product it with the test neighbors covariance matrix, which was 1 cross 10. Once we have that, we will find out, we will get the weights for what we call the neighboring samples. Given the weight, we will use a weighted average. We will do the weighted average prediction as we do in simple nearest neighbors. So the most important part is basically finding out this weight using this covariance matrices, and this covariance matrices are calculated using Variogram model, and this Variogram model was calculated basically using these semivariance values, and these semivariance values were calculated basically using pairwise distances. I think so it's clear now. Let me encode it in Python. Let's see it in action. Okay, so we will begin with the variogram modeling. For variogram modeling, we will look at the pairwise distances. So this is like samples in x-axis, this is the y-axis, this is the grades. So these are total number of samples. This is initialization of change in grade, change in x, change in y. For all of the samples, we will look at the change in grade, change in x, change in y, and we will store it in the dictionary and we will return it. Then we will define a skip diagonal masking function where we will calculate the identity matrix of Boolean type, and we will take all the elements of the arrays except that identity matrix. So this will be like skip diagonal masking. Then we will calculate the angle azimuth array. For that we will first of all apply the pairwise differences as we have done it. This function that we have explained, we will apply it. Once we apply that, we will extract the change in grade, change in x, change in y information. We will skip the diagonal matrices for change in x and change in y matrices. Then we will use y. Then we will calculate the angles with northing using this formula, where change in y divided by change in x is will be stored in y exchange. And for quadrant number 1 and 4, we will be using this formula numpy dot pi into, you can look at, you can search it, or you can search it in internet. So this is a way of finding out the grade with northing. Once we found that, then we will be looking at azimuth array where change in x is greater than equal to 0. So wherever it is greater than equal to 0, so we will use it for grade number 1 and 4. If it is not greater than equal to 0, then it means it lies on the other side of the quadrant, which is in quadrant 2 and 3. So for quadrant number 2 and 3, we will be using this value, and for quadrant number 1 and 4, we will be using this value. How will we find out the quadrant number? We will look at the change in x. If it is greater than equal to 0, so it means we are in the quadrant number 1 or 4. If it is not, then we are in quadrant number 2 or 3. Okay, so then we will calculate the distance between training sample. This will be 470, 470 matrix. Given the metric will be Euclidean. Then we will calculate the semi-variogram. For semi-variogram, what we are given is the x direction, y direction. These two are the input dimensions. Then we are given the input azimuth for which we want to calculate the semi-variogram. Consider we are given azimuth of 0 degree and the tolerance of 10 degrees. So so as explained in the video, it will be 352 10. Then we will be given also the lag distance for which we want to find out the pairwise samples. Then also there is a lag tolerance. Then the metric is actually Euclidean metric, a distance metric. Then what we will do is, first of all, we will find out the coordinates. This will be like x and y. So this is like the same thing, the x and y concatenated together. So it will be having two features, x and y, this coordinate matrix. Then we will find out the distances between the coordinates. Then we will skip the diagonal matrix for the training samples or the coordinates. These both are the same things, coordinates and the training sample. We are calling it coordinates here. Otherwise, they are basically training samples. Then we will find out the azimuth array and the change in grade as we have used this function that I explained earlier. Now, all of these things have been already explained. Now, after calculating this azimuth array containing the angle of all the samples with northing and the change in grade, what we will do is we will skip the diagonal matrix for the change in grade matrix. Then we will find out the maximum distance, and then using the maximum distance and the lag distance, we will look at the number of lags. In the example that I explained, the total number of lags were 10. Given the lag distance of 10 and the maximum distance of 100, 100 divided by 10 is equal to n. So there are totally 10 lag distances, and we will be using total. We will be getting actually 10 values, and we will iterate it over here. I'll explain this iteration. But before that, we will also look at the minimum lag distance, like the minimum range of angle and maximum range. So this will be used for extracting the pair of samples, which actually satisfies the condition of lag and azimuth, as I explained earlier. Okay, once these conditions are confirmed, so what we will do is it will output the pairs 1, pairs 2, pairs 3, pairs 4. These arrays will be containing value of either 1 or 0. If the condition is satisfied, then it is 1, otherwise it is 0. So we want to extract all the pairs which are actually satisfying all of the 4 conditions. For that reason, we multiply all of these matrices. So samples containing 1 at all of the 4 pairs of matrices will be retained, otherwise all of the other pairs will get the value of 0. So then we will look at the total pair count. We will extract the change in grade for those pairs, and we will sum it, and we will divide both of these values together, and then that is what we will call the region variance. And that variance, once multiplied by 0.5, that is what we call semivariance. So this semivariance will be calculated for each of the lag and will be appended in the list, and finally we will output this semivariance list. Given this semivariance list, and now these are some helper function to find out the lag distance function and all lags, which will be used in variogram models. But basically there is no concept given here, but this is like basically just getting the lag distances out and looking at all lags, like the list of all lags, which will be used later. Okay, so in variogram model, what we need is this CIL, this nugget, this maximum range, and variogram type. So all these 3 values will be taken as an input and will be received from after plotting this semi-variogram values stored in this list, as we already explained. Now, given the CIL, nugget, max range and data, we want to know the CIL contribution, which is equal to CIL minus nugget value, and then we will based on the variogram type, if it is spherical, then this is the formula for fitting the model. So this is that line which we fitted on the semi-variogram. This is the formula for that. So you can look at it in internet and you can find it. For Gaussian, the formula is different, and for exponential the formula is different. When do we use which one? There is not much of a difference, but yes, of course there is a difference. You can look at the details of that. Okay, now we fit the variogram model by, first of all, getting all the lags. And how do we get all the lags? Using this function where we are just making use of this lag distance, this basic lag distance and number of lags to find out all the lag values. So given the all lag values, what we do is we fit the variogram model and we return this model variance for all the lag values, all the intermediate values from 10 to 100 that we already explained. Now comes the Kriging part. This is making use of variogram where we extract the weights. So first of all, this is great. Given if we are given the test point, 78,000 test point, then there is no need of it. But if we are not given, then given x and y, and then we can create the grid, which is regularly spaced at cell size x and cell size y. So I mean, simple grid calculation using the numpy.mesh grid function. Then we extract the search neighborhood. This part is again just replication of the previous function where we calculate the grid, and this is basically train coordinates or training samples. Now here we know, here we are given the radius. Given the radius, we calculate the distance between testing and training samples, and we look at this matrix. Consider we have testing point 78,000 testing points and 470 training points, so the matrix will be 78,000, 470. In this matrix, if the radius is less than equal to this value that we are given as an input, then we return true, otherwise false. Then for each of this test point or test grid, what we do is we extract the train data based on this temporary array value, which is true for neighbors and false for samples which are not in search radius or in neighbor. So we extract the test neighbors, and then we calculate the distance matrix. And how do we calculate that? It's quite easy. I mean, first of all, after calculating this test neighbors, we look at the neighbors pairwise distances. We extract the neighbors pairwise distances and neighbors test distances. This is what I explained. We will be using both of these distances to calculate the relevant covariance matrices. Now we are making use of distance.c distance function, which you can look at scipy, and they are just taking these as an input and retrieving and returning these distance matrices. Once done, we will make use of this variogram model These are again input, and this is variogram model that we received, and we are for neighbors pairwise covariance distances, we are making use of this loop, and for pairwise neighbors and test sample point, we are making use of this loop. So in this loop, first of all, we are extracting the covariance matrix, we are adding the Lagrange parameter, one's column, one's row, and we are making equal the zero, the last extreme left and extreme bottom value, and whatever the value that we received, we actually store it, the covariance matrix, we store that covariance matrix that we calculated, and the same thing we do it for the test neighbor covariance matrix. We add the Lagrange parameter, and then we retrieve this covariance matrix also. At prediction time, what we do is we have already calculated this function. At prediction time, for each of the test sample, what we do is we take the inverse of the neighbors pairwise covariance matrix and the neighbors test, and then we take a dot product of that inverse neighbors pairwise covariance matrix with the test neighbors covariance matrix. And then that will give us the neighbors weights. Using those neighbors weights, we will we will remove that Lagrange term, and then we will use those weights to find out the weighted sum of neighbors, like a weighted average. So this will be our final predicted value. All of these function and all of these details I have already explained. I've just shown you the implementation part. As far as the explanation of what it is has already been explained. So if you understand the previous workbook, previous whiteboard explanation, then I mean there should not be any problem in understanding of this code. I hope so this makes sense now.